So let's start by just thinking about how to find the area, not of a 3D, not a volume, but the area of just simply like a washer shape. So if I have this picture here, and I'm trying to find the area of this donut right here in the middle. Right, so the blue shaded with that beautiful blue shading there. I want to find the area of just that blue shaded region. Okay? So, and this is 2 inches here in the middle. This is 4 inches here. And this part right here is 4 inches as well, although it's not going to be needed. Alright, so if I want to find the area here, I'm going to take the area of the outside circle, which in this case, what's the radius here? 6. Area all the way to the edge, you'd have to do that 4 plus the 2 in the middle. So pi times 6 squared would give us the area of this outside circle. And then we would have to,
Why is the radius 5?
because that's a 2. Is, yes.
There's another 4.
We don't care about that one because we're only looking for the blue area. I could have left that circle off, really.
Oh, I thought it was excluding the blue area.
We want to find the blue area. All right, and then so we would need to subtract the hole in the middle. So that would be pi times 2 squared. So that'd be 36 pi minus 4 pi, and we would get 34 pi as our answer. Pretty much. I could have left it off of the picture. Yes. Sorry. Because that would be the area of that middle piece right there. If I could subtract correctly, we would get 32 pi. No bathroom passes for live mistakes like this. I make too many of them. All right. All right. Please do not recap right now. It's probably not appropriate. All right. So, all right. So, for the washer method, I'm actually going to write it. So, whenever we're looking at finding the volume, it is a very similar process. We want to find the volume of the sort of outside shell and pretend there was no hole. And then we'll find the volume of the inside part. All right, so here's my last example of my woodworking. This is not my woodworking. I did not make this. If I did make it, I would be proud of it, but I did not. Because that probably, if it wasn't made with a machine, it was actually probably very impressive. I bet it was made with a machine. Foster Manufacturing Company in Plano, Texas. If you are looking at this piece, you would want to find the volume of the outside part, like there is no hole at all, like it's flat, like there's no hole. Then you could find the volume of the empty space in the middle, and you would subtract it away. Okay? So it's like you're finding the volume of 2 separate entities and just subtracting. Right. And it's really important here. So what we could not do here is on this problem, we could not just do 4 minus 2. Like we couldn't take our radius and just do 4 minus 2. That gives you a radius of 2. And then do pi times 2 squared. That would not work because it would give you something entirely different than what you're looking at. So we have to do the nothing really. In this case, it ends up being the area of the hole in the middle, but that's just sort of coincidence for this case. I have written the washer method here. This is what's used a lot of times, but I would suggest thinking about it this way. You may want to add this here. I would suggest thinking about it this way. The integral of pi times big R of x squared minus the integral from a to b of pi little r of x squared. But they should have dx's with them. So it's sometimes helpful to think about this like you're doing the two problems separately, outside and then inside. However, if you've got to actually calculate it by hand and not just set it up, this is going to be easier to calculate because you'll combine some stuff before you do the calculations. So we'll work from this, but if we have to actually calculate it by hand, we'll pull out the pi and combine those two pieces there. And I have used the big R for the outside radius and the little r for the inside radius. You'll also may notice that we skipped 8.10. We are going to do 8.10 and 8.12 together tomorrow. So that is the reason. Yeah, both of them are just like these, but rotating around different axes, like x equals 3 instead of the x-axis or something like that. It's going to change it, but it's not too bad. It's not too bad. If you understand this, it's not too bad. All right, so let's look at example 1. All right, find the volume. Daniel, quit talking. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. So we need to think about these two graphs because this would be calculator inactive probably. At least the setup part would be calculator inactive. So it's just going to be first quadrant. And where are they going to intersect? 0, 0. Where else? 1, 1. 1, 1. Because if I plug in 1, square root of 1 is 1. And if I plug in 1 over here, 1 squared is also 1. So they're going to intersect at 0, 0 and 1, 1. So it's really helpful here to know what those graphs look like, because otherwise it makes it difficult to know which graph is on top, especially since this is calculator inactive. And if you try to plug in 1/2, you got to compare the square root of 1/2 and 1/2 squared, which is not easy to do without a calculator. So we should know that x squared, I'm going to do it in red, should look like this. They did tell us, well, they didn't tell us first quadrant, but x, the square root of x, I'm going to do that in green, it would start here and it would have this shape. Yes. All right, and so we are revolving around the x-axis. So we are going to be doing everything in terms of x for this. So what we're taking this area right here, and we are going to revolve that around the x-axis. So let me try to do this, but it's so hard to draw, I might just mess it up. So it would be like we took a little section here, and on the inside, we would have this part of the circle, the outside would go like that. If you can visualize that, so that the whichever function is closest to the x-axis, whichever is closest to the x-axis, that part's going to cause the hole. And then the outside gives you like the actually filled in area on the outside. All right. So our capital R, our radius, our outside radius, it needs to be the function furthest away from whichever axis you're rotating around. So in this case, it is our square root of x. And our lowercase r, that's the radius of the whatever's closest to the axis that we're rotating around. That is going to be the x squared. So we can think of, so when it's like you're doing two separate problems. So it's almost like you're ignoring that it's going to be this area, this in between here. We're taking, for the outside radius, it would be from that outside piece all the way to the middle. Whereas here, for the inside radius, it would be, inside part all the way to the middle. That equation will give you the radius at any point on that line. Yeah. So like if I wanted to know at 1/2, I could plug in 1/2 and I'd figure out what that radius is at that point. But because it changes between 0 and 1, where your graph is increasing there, you just use that equation for that radius. So if I want to find the volume of the outside part of the figure, then I would integrate from, limits are going to be easy on this one, because even if you mess it up, you should get it right, because they're the same on the x and the y-axis, but we're looking at the x-axis here, 0 to 1. And we will do pi times big R, so square root of x squared. That would give us the volume, and put a dx there. That would give us the volume of the outside part, but we must subtract the volume of the empty space in the middle of the shape you get from the whole part of the function. So that would be the integral from 0 to 1 of pi times x squared. I like setting it up separate like this at first just because it helps me remember all of the pieces. If you like skipping steps a lot, because these have the same limits, I can combine them. Both of them have pi, so I could pull the pi out front. And then I would integrate from 0 to 1, and I would have the square root of x squared minus x squared dx. You don't have to write this part that I just wrote here. What I find is students forget this pi really, really badly if they go ahead and put that together. Or they square these together. They write it like this, square root of x minus x squared, which would be wrong. You have to square them separately. You can work them out separately and combine them. It makes it a little faster to do if you put them together first, but it doesn't really matter. So this one's not terribly bad because this is really just x minus x to the 4th. So whenever we integrate that, we'll get 1/2 x squared minus 1/5 x to the 5th. But thankfully, we just have to plug in 0 and 1, which is just going to be, we'll get 1/2 minus 1/5. And then when you plug in 0, you just get 0 there. So 1/2 minus 1/5 is 5/10 minus 2/10 just going to give 3/10. So we'll get 3/10 pi, or 3 pi over 10. I think these are so cool. I like them. Even though it's hard for me to picture them sometimes, but I like these. Yeah. 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 Have more trouble with cross sections than these. Yeah, the cross section ones. Yeah. I wouldn't necessarily call them easy. Yeah. All right. Okay. Here's example 2. All right, we got to find the volume of the region bounded by the graphs of f of x equals square root of x plus 1 and x squared plus 1 when they are rotated about the x-axis and the y-axis. We're going to do x-axis first. I know, I'm sorry. I should have put some space on that. Sorry. All right. Okay. All right, so let's think about what's going to happen here. So we've got the square root of x plus 1. So we're going to have the square root of x plus 1 will look like this. And the x squared plus 1 will look like this. And they should intersect right there. Let's make that point right there is 1, 2, even though it doesn't quite look like it is. All right, so that is the exact same shape we just had. Is it going to give us the same volume when we rotate it around? Okay, it is not, because the hole in the middle is bigger this time, right? So, and the outside part is going to be bigger because it's further away from the x-axis. So if they asked us just to find the area between those two curves, it would be the same if we were doing the first question or this question. But whenever we've got to rotate it, it's going to make a difference that it's further away from that x-axis. So, we are taking a little sliver like this. We're rotating it around our x-axis like so. So our outside radius, our capital R of x, is our equation furthest away from that x-axis. So that is going to be the square root of x plus 1. And our lowercase r of x, our inside radius, is going to be x squared plus 1. So if we want to find this area, we've got to do pi times that radius squared. What should my limits be here? 0 to 1. I'm pulling those from the x-axis because we're rotating around the x-axis. And then I would subtract our integral from 0 to 1 of pi times the inside radius squared. If you have this one, you mostly want to rely on just the graph and plugging in numbers if you need to. If you have other ones that you're not sure, you can set them equal to each other. The problem with this one is you got square root of x plus 1 equals x squared plus 1. So even though it's not, well, I mean, you're going to subtract the ones, they go away, so you get square root of x equals x squared. Square both sides, x equals x to the fourth. You could move the x over, x to the fourth minus x, and factor out the x cubed minus 1. So you'll get x equals 0 and x cubed equals 1. And so that would be your 0 and 1. So you can set them equal to each other to find those intersection points. Sometimes that's harder than actually just like graphing the points, though. So it just depends on what you're given. If they're calculator active ones, you would just want to set them equal in your calculator and solve those. Or you could look at the graph if they're y equals ones. All right, so let's put the pi out front. I'm going to combine these, but we need to be careful when we do this. Oh. How far are we going to go with this? Should we just practice our calculator skills? Yes, let's just do it. Too far in? I'm just going to practice my calculator skills. I don't think you're going to see. So, I don't think you're going to be asked to integrate this one by hand on the actual AP exam. I think they would probably only ask you to set up or put it on calculator active here. So, you just have to be really careful with parentheses when you put this in. So, you got your pi out front. We are integrating. You can put this in y1 and y2, and then you just have to do y1 minus y1 squared minus y2 squared. Sometimes I find it helpful because you don't have so many parentheses in one place if you do it that way, but it's just sort of a preference on these. Now, I will say if it is a calculator active free response, put them in y equals, just because they're probably going to ask you other questions about them. So we've got square root of x, close the parentheses for square root, plus 1, close the parentheses here, and square that, minus x squared plus 1, close that parentheses, square that, comma, x, comma, 0, comma, 1. Let's see if I got it. So I got 29 pi over 30. Okay, by
Which is 3.037.
correct. All right, so what'd you guys get? I think I've got everything in right. Let's see. Okay. Check and see right here. Make sure that your square root stops in the right place. Make sure it looks like it's supposed to look on this line. All right, so that's x-axis, which since we did the calculator here, I'm gonna move this back up here. Now you should have some room for your y-axis, even though it's down here at the bottom. All right, so y-axis. When we think about this with the y-axis, we still have the same graph. But this time, we will be taking a horizontal section and we're rotating it around the y-axis. So, to do this, our equations have to be solved for y. So we've got y equals the square root of x plus 1. So that's y minus 1 equals square root of x. And we would square both sides, so we get y minus 1 squared equals x. Now, be really careful here. I'm going to label this over here. That is my blue graph. This blue graph here is x equals y minus 1 squared. Once I have solved them for y, I'm really bad to get them mixed up because I forget which one is which. So I would label it over. It will, yeah. Correct, yes. So that blue graph is going to be our little r here. It's closest to the axis that we're rotating around. And then my other one, y equals x squared plus 1. That's going to be y minus 1 equals x squared. So x is going to equal the plus or minus square root of y minus 1. But we can't really do that with the plus or minus. Which one should I pick? I'll pick the plus because it's on the positive side of the x-axis. So this red graph right here, that is x equals the square root of y minus 1. So this time we're rotating around that x-axis. Our outside radius is the red graph. So that capital R of x is this, or actually, what did I do wrong there? It should be R of y, because we're in terms of y. Probably not if you get it set up correctly after that, but it would be better to call it capital R of y and lowercase r of y. So this will give you y minus 1 squared. So, integrals, I like to set them up separately. But if you don't, that's okay. What are our limits on our integrals here? 1 to 2, because we're looking at our y-axis here. The dy with that. And so I'm going to combine these. I'll pull the pi out front. And I will have the square root of y minus 1 squared is just going to be y minus 1. And then I will have y minus 1 squared squared. So that's going to be y minus 1 to the 4th power. Hopefully they are not going to give you this without a calculator either. They'll either hopefully just ask you for setup or give you the calculator, because raising that to the 4th power, you can use Pascal's triangle. So let's just use the calculator here though. Oh wait. Y minus 1 plus y minus 1 to the 4th, comma y, comma 1, comma 2. Alright, and we get 3 pi over 10, if I did that right. The homework for tonight, guys, will be from the same pages that we had last night. It's just going to be different numbers. It's on Canvas already. Good luck. Hope y'all win. All right. Yeah, we've just got 2 more sections. We got to do 8:10 and 8:12, which we were going to do both of those tomorrow. And that will be the last new material that I'm going to teach.
We're not gonna like take a break.
We'll see.
Like review, like they're eating cookies in class. Yeah, because it's right across the street.
February 12th. Can't remember. If you didn't, I wasn't offended, huh? I don't remember. Maybe not. Thanks. All right, so it was a Saturday this year. It was a Saturday. Really? Your brother has the same birthday? Oh, it's a good birthday. I like February is a good month. Well, it's a good month for a birthday. I feel like there's fewer days, so you're less likely to be born in February. So if you are born in February, it makes you just a little bit more special than everyone else. Yeah, leap year is the coolest, though. I think that is the coolest birthday that you can have. Or leap day, I guess. Yeah, Christmas, that one's not great. Yeah, Henry's is the 7th of December, and that's still too close to Christmas. Yeah. My sister-in-law, hers is the 26th. Day after Christmas might actually be even worse than Christmas. Yeah. So, even though, when you grow up and have children, if you have a kid, anytime during the year, you get the full tax write-off for that kid, even if they only were, actually born one day of that year. So my Henry was pretty good. I didn't realize that. So we got the full tax write-off that next year, even though he was born December 7th. But my nephew, he was born on December 30th. So they only really had him one day of the whole year and got the full tax write-off for him. So that was good. If the tax write-offs are your primary goal, even though I guess it kind of they'll probably, when you turn 18 or, I'm not sure. You can still claim them longer if they're in school, but I don't think it's like the child tax credit, the big. Yeah, they can definitely stay on your insurance. But whenever you quit being able to get that credit, I guess it's going to stop a year earlier, so it probably evens out. But it's nice that one year. Because we got a big refund that year because I wasn't expecting us to get I didn't know that. So, yeah, so that's the only good thing about having a kid really close to Christmas is you get a good tax write-off. Not the only good thing about having a kid, period, is tax write-offs. But having a kid close to Christmas, you get a good tax write-off for it. That's your little bonus. Yeah. Henry's is December 7th. Hunter's February 18th. Yeah, he practically stole my birthday because, even though it's not the same birthday, nobody pays attention to mine anymore. I wanted him to be born on my birthday because he was due the 8th, but he was 10 days late. He was only 7 pounds 8 ounces, so he was not a gigantic baby, but probably not. Probably not. I would get more tax write-offs. I mean, that is a consideration. You know, like, yeah, let's no. You can't do that. You don't. Yeah, you can't give them back and still get the tax write-off. I don't think. So October 29th. So, yeah. His birthday is February 26th. Where he's registered, I get emails that remind me when his birthday is. That's how I remembered this year. Tux. Yeah. Really? I think some people get blood tests and stuff if they really care about it being full bred. They'll get blood tests with the certification to double check that it's really, really. We need to fix this problem. We got Tux from Doggy Style Kennels in Charlotte. That was the name of the kennels that we got Tux from. We were a little weary, but she was actually great to work with. She was really nice and sends pictures, and he's been healthy dogs. We could not find one anywhere else, so we just went with it. I would recommend them if you're looking for a Boston Terrier. Okay. Okay, let's look at this problem. All right, so this last one here, I'm not doing the calculator active ones on the notes today because it's the same idea, but they're a little bit easier to do because you can graph them and you can use the calculator to integrate. So this is sort of the upper limits of what you would see without a calculator as far as setup. I'm not sure they would ask you to integrate it without a calculator, but they might ask you to set it up without having a calculator. So we could get a graph of this. I know this is a quadratic. I know it's a smiley face one. I could find the x-intercepts if I wanted. They're going to be 0 and 4. I know this is a line right here, but it might be a little hard to graph, especially without graph paper. So another option that you have is you can just set these equal to each other. And you're going to find those intersection points, and then you can put a number in to see which one's furthest away from the x-axis and which one's closest. So if we move everything to one side here, yeah. So we'll get x minus 4, x minus 1. So we'll get x equals 4 and x equals 1. So those are going to be your limits of integration there. And then to know which one is the function furthest away from the x-axis and which one's closest to the x-axis, we can just pick a number between 1 and 4 and plug it in. So if I plug in 2 here, I'll get 2 squared minus 4 times 2, which is going to give us negative 8. No, not negative 8. 4. Negative 4. And here I will get 2 minus 4, which will give me negative 2. So let's think about what we're dealing with here then, because I wasn't necessarily expecting negative numbers there. This is a quadratic here, and then I've got a line with a y-intercept at negative 4, and I guess it's going to look something like that here. Actually, I think it's actually going to hit the x-axis right there. They're going to have the same. It doesn't matter really for your setup though. Yes. Yes. Yeah, so like this would, at 2, wherever 2's at, about, I guess it would be sort of right here, you would have a -4 on your quadratic and a -2 on your line. So we're taking this area, which is actually below the x-axis, and we are going to take that and spin that around the x-axis here, so that the lowest number is actually the one furthest away, since this is below the x-axis. So the quadratic is furthest away, so we're going to call that capital R of x is going to be our x squared minus 4x. And then the lowercase r of x is going to be the x minus 4. And technically that's giving you like a negative radius, but it doesn't really matter, because when you do pi r squared, since the radius is being squared, even though it's giving you that negative below the x-axis, it's going to become positive. So it'll still give you the right answer. So we would set up here, we would integrate from, what are our limits? 1 to 4, and we'd be doing pi r squared, so pi times x squared minus 4x squared minus, and then we can integrate from 1 to 4, pi x minus 4. Because the formula we're using for this, whenever we rotate that around the x-axis, it's going to create a circle. So we're using the formula pi times the radius squared. Oh, dx. And I should put the dx's here. Let's put this all together here. It's just easier to type. I'm going to use the calculator to get the number answer for this. It's easier to type it in if you do that. X squared minus 4x squared minus x minus 4 squared. I think they would either, if it was calculator inactive, they would just ask you to set it up so your answer would look like this. If it's calculator active, we wouldn't have to worry about that graphing part at the beginning. But so we get 108 pi over 5. Or you could do the decimal. $67.858. I kind of like these two. You're always dealing with the same formula for this. You don't really have to think too much about the formula, so I think that's helpful. Yes. So you always want to go furthest away from the axis of rotation and then closest to the axis of rotation. Okay, so assignment is from the book. It is these problems similar to what you had last night. Make sure you write down your setup. It is okay with me if you integrate using the calculator, because I don't want you to spend hours on this homework trying to integrate some of these by hand. Some of them aren't bad, but some of them will take a while if you try to do them by hand. No. Yeah, the 13 we did, but we only did part.